So we're going to look at what is work, and we're going to get into what is power and what's machines and how are they measured. So here we go. What is work? Well, work is a force applied to an object through a distance. So work equals force times distance. And force is in newtons and distance is in meters. So we abbreviate that to form a joule. 1 newton times 1 meter is the definition of what 1 joule is. So work equals force times distance. So, but here's the catch. The work, the force in the object's motion must be in the same direction. Okay, that's a big deal. So if I lift my phone up, my force is applying up and my movement is going up and I'm doing work. But if I were just holding my phone up, my force is this direction, but I'm moving it towards the computer screen at 90 degrees, I'm actually not doing any work because they're not going in the same direction. They're going at right angles to each other. And when they're going at right angles to each other, no work's being done. So, contrary to popular belief, when you have to carry the groceries in, the only time you do work is when you lift the bag up and when you set it down. But when you carry it, you're just applying a force. And again, work is measured in joules. So this would be another handy dandy thing to add to that formula sheet that you've got started. So, do you do more work when you finish a job more quickly? Does time have any element in that equation? Well, it doesn't. Work does not involve time. There's no part in this equation where time comes into play. So doing a job more quickly does not mean you're doing more work. You're just shortening up the time period, but the work is the same. And no work is done if you stand in place holding an object. That's just, like I said, carrying the phone. That's just holding the phone. As long as you're at right angles to each other in the direction of motion and the application of force, no work. They both have to be in the same direction, whichever way you tend to go. Would you do more work if you ran up the stairs 2 at a time? Well, you're going to get there quicker, but you are going a greater distance, so that's an interesting question that we'll explore. Who is this joule? Well, 1 Newton meter is a quantity known as joule, who is named after a British physicist, James Prescott Joule. He's the one that figured out this formula, so it gets to be named after this individual. All right, so one of the things you're going to end up doing on an assignment is deciding if we've done work or if we haven't done work. So if I am mowing a lawn, now it's not at 90 degrees, I'm at about 45, so it's not as efficient as if I could push it straight, but it's easier because we don't have to like crawl on the ground to push it parallel to the ground. So yes, I'm doing work when I mow the lawn. If I'm lifting weights, yes, as I lift the weight up, I'm applying a force in the same direction the weight is moving. Moving furnitures up a flight of stairs, yep. Pushing against a locked door, no, that's just applying a force. I'm not moving the door any distance. If the door opened, I would be doing work on the door, but it's not. Swinging a golf club, yeah, I'm doing some work. Power is the next quantity we want to talk about. So power takes into account time. Remember how I said work doesn't? Power does. So if I take work and compare the work to time, now that's power. How quickly work is done is power. The amount of work done per unit of time is power. If 2 people mow 2 lawns in equal size and one does the job in half the time, who did more work? They both did the same amount of work, but one used more power. A more powerful engine can get you there quicker. So the difference is between work and power is the time factor. So Watt, a Scottish inventor named James Watt, he's the one that invented the steam engine. And he's the one that figured out that power's relationship to work and time is a joule per second. So 1 watt is equal to 1 joule per second. Obviously, we're going to practice a little bit of this math. This is just the intro to understanding, but this is where you should be putting this stuff in your notes. Putting in what power is, that it's a joule per second. Putting in that work is What? Well, if you don't remember, this is when you go back and look. It's really important that you know that work is force in newtons and distance in meters, which is 1 joule, because you need to know what a joule is if you need to calculate stuff backwards. Therefore, you need to know, once you get into this handy dandy power equals work times time, understanding that this is in joules per second, which is a newton per meter per second. All right, and if you don't forget that, Newton meter per second, otherwise known as joules per second. So always go back to the notes if you need to, but more importantly, please put this on your formula sheet. All right, let's go past the watt. And watt is used to measure power. So how many watts a light bulb is how much power is going through it. The greater the power, the more kilowatts used, the greater the cost. 1 kilowatt is 1,000 watts. Kilo means 1,000. 1,000 what? 1,000 watts. Not 1,000 meters, that's a distance. In this case, a kilowatt is the amount of power. It's just 1,000 units of that power. Horsepower is equal to, get this, the horse that can pull a wagon is equivalent to 745.5 watts. So traditionally associated with engines, cars, motorcycles, lawnmowers, even my Vitamix blender, I'm not promoting it, but it's actually measured in horsepower. The term horsepower then was developed to qualify or quantify power. A strong horse could move 750 newtons objects 1 meter in 1 second. So this is the throwback to the carriage. More horses meant more power. They could get there faster. Each horse had to do less work in a given time. So machines, devices that make work easier for us. A machine can change the size, the directions, or the distance over which a force is acting. We've kind of talked about this a little bit before. It's a really big definition. It can change the size, the direction, or the distance over which a force acts. Forces are involved in input and output. So what kind of forces do I put into the machine determines what kind of forces I can get out of the machine. So we do that as force, the big F, and then we do those subscript things again to qualify which force we're talking about. In this case, on this side, it's the input force. On this side, it's the output force. So it's F sub I or F sub O. Force applied to the machine, input. Force, applied coming out of the by the machine, or out, is the output force. Again, good things to define on your formula sheet. What is F sub I? What is F sub O? Input versus output. So, two forces, thus two types of work. Input work and output work. So now we've got W sub I and W sub O. You could put that if you wanted to on your formula sheet as well. Input work versus output work. Work done on the machine is input work. Work done by the machine is output work. So input force times the distance through which the force acts is input distance. Conversely, output force times the distance through which the resistance moves is output. So in other words, if I push on the machine and make the button go, there might be a mechanism inside. Maybe it's a pulley, maybe it's a simple shape machine, maybe it's a lever. As I push down on one side, what is its resistance? What is it moving on the other side? So when force or distance is changed on one side of the machine, it's oppositely affected by the other side. So if I make force big on the input, on the output, distance becomes big. And conversely, if I made distance big on the input, my force would be bigger. So it's kind of like we're running a block and tackle pulley system. If I make that rope go through 5 different pulleys, it's, that's 10 times the length at least. But I can lift a heavier object with one little tiny finger. So if I trade distance, if I pull something really far, I can lift heavy objects. Or if I apply a lot of force, I can make something move through a distance quite quickly. So this is an important relationship in force and distance. for input and output work. As one gets bigger, the other one has to get smaller, and it's the opposite on the other side. Can you get more work out than you put in? Workout can never be greater than work in. You're always trading off distance and force. So if I put more force in, I can get more distance out, but my force at the end has to be reduced. These can be equal, but we don't live in a perfect world. We have frictions and resistance and things like that. So usually the output is a little less than what you put in one form or the other. So what you need to do on this one now is tell me what is the difference between power and work. This is where you need to remember that work takes into account what two things? Power takes those two things into account over a given amount of time. And this is where, if you don't remember, you should go to the notes at the top of this page where you're filling this out and go back and look at the formulas. Work is the product of force times distance. Power, which is a joule, power is taking that joule times time per second. So work is force times distance. Power takes into account time. As always, if you need help or this doesn't make sense, ask.